Okay, so last time we met, we talked about how to analyze systems of two nonlinear differential equations. I'm just going to turn this down. And we call the approach a phase plane analysis. I'm quickly going to review that. So in your textbook, we write the equation dx dt is some function of x and y, and dy dt is another function g of x and y. Last time I used capital F and capital G because I used little f and little g for the per capita rates. But in the textbook, you'll just find it written like this. So if we're going to carry out a phase plane analysis of this model, what's the first thing we're going to do? What's the first step? Yeah? Not find the derivative. Yeah? You solve for fx, y equals 0. You find, okay. So we look at f of x, y equals 0, and gxy equals 0. So step 2 is plot the lines that arise from this. So plot null isoclines. So for example, if we look at this equation, typically what happens in the phase plane, and remember, for the systems that we're interested in, we're usually just interested in the positive quadrant. So here we have x, and here we have y. And usually this will lead to an isocline x equals 0, typically, although not necessarily, and then some other isocline, whatever. And so this is f xy equals 0. But this is not the case. X not equal to 0, because that's that one. And then we do the same for the other one. And typically that's y equals 0, or we might get something else, like that. So we've now plotted the isoclines, and that's the x null isocline and the y null isocline. And from this, we can identify the equilibria of this model. So where are the equilibria? Yeah? Okay, the two lines of different colors. Yeah. So there, not over here, and over here, for example. So what's the next thing we do? So the next thing we do is we have a look. fxy equals 0 means that on one side of the line, fxi is going to be greater than 0, and on the other side it's going to be less than 0. If fxy is greater than 0, it means x is growing. So we can test out a few, we can look at the expression, and we can decide what's going to happen. If x is growing on one side and is declining on the other, then I can do something like this. Here you can see I've got 4 different regions that I've identified. Now what I've got to do is I've got to decide where is x growing and where is x declining. So I've got to decide, is fxy positive or negative here? If it's positive below the line, then it'll be growing below the line and declining above the line. So I can draw arrows like that. Now do the same with gxy. So I'm not sure yet where to put the arrows. So on one side of the blue line, the arrows will go in one direction, and on the other side, they'll go in the other direction. So let's say, for example, in this case, they go above the blue line. Let's say the system is declining. And below the blue line, the system is growing. And then if I look at the resultant of these processes at each one of these points, I would say the system is going in this direction over here, and this direction over here, this direction over here, and this direction over here. So from that, you can work out what the system's going to be doing, and then we can draw some trajectories. So what I'm going to do now is I'm going to do this in the case of a simple example, so that will make this all real. And the example I'm going to look at is what is called the Lotka-Volterra equations for predation. So we're going to look at the Lotka-Volterra prey-predator equations. In some places you may see that they talk about predator-prey equations. We talk about prey-predator because typically we represent the prey by x and the predator by y, and so just by convention we list the x variable first. So x is the density of prey and y is the density of predators. And so we're going to write down an equation for x, dx dt, and dy dt. And so the first assumption I make is that in the absence of predators, the prey grow exponentially at a rate a. So since if the predators are not there, the population is growing exponentially. Now obviously, this is not a good assumption when the population gets very large, because it can't just keep growing without bounds. But what we're going to ask ourselves is, are the predators enough to control the prey? So when you see a population out in the real world, and it doesn't matter whether it's wolves in Yellowstone, or bison in Yellowstone, or elephants in Africa, you say, what is the mechanism by which these populations are constrained, their growth is constrained? Is it constrained by disease? Is it constrained by predation? Is it constrained by limited resources? If a population is constrained by limited resources, then what's the appropriate starting place for modeling that population? If we're using a differential equation like this. So, okay, well, let's start first if it's not constrained. If it's not constrained and it's growing exponentially and the per capita rate is A, the per capita growth rate, then what do I write on the right-hand side to capture that idea? AX, right. So the population is growing exponentially, that's what it looks like. If it's constrained by resources, how would I modify that? I would use a logistic equation, so I'd write something like 1 minus x upon k. So it's not out there. But if I say I'm going to assume the population's growing exponentially, is there a mechanism by which it can be constrained that is not the resources, but let's say is a predator? So the predator is like a harvester. The predator comes along and says, I'm extracting prey from the population. It's like I'm harvesting the population. Humans are a predator on fish. So with humans, we had BXV, where V was the effort level. We actually had QXV. That was our fisheries model. But now we're saying it's not humans, it's not the V that counts, it's the predator Y, the density of the predator Y. So instead of having an effort level, we actually replace the population because we say every individual in the population is making an effort to catch the prey. Because everybody has to go out and get food. And instead of Q, I'm just going to use a B here. So that's an assumption on, and what that assumption says, it's called the mass action assumption. It's called mass action because you can think of X and Y, if they measure the density of prey and predators, then X times Y is kind of a frequency at the measure they will interact. If things are interacting at random, if you've got red and blue billiard balls knocking around on a billiard table, how many times does a red billiard ball knock into a blue billiard ball? Well, if you've got no red billiard balls, you get no encounters. If you've got no blue billiard balls, you get no encounters. The encounter rate is proportional to the density of both. So this is called mass action. And this is quite common in physics and in chemistry. If you assume rates at which substrates interact, if you have a look in a chemical process and you've got two substrates, or an enzyme and a substrate, and you say what's the rate at which they interact at a rate proportional to their concentration. But here we talk about density rather than concentration. But in chemistry, you would write down equations like this, we talk about concentration. And this is exponential growth of the prey. And now we make the assumption that the predator, in the absence of the prey, if you don't take the prey into account, they're going to decay exponentially. And let's say the per capita decay rate is C. So what would the term be on the predator equation, the first term, if they decay exponentially? Yeah, so it would be negative CY. Okay. Now you have to ask, is that a reasonable thing to assume or not? What do you think? If there's no food around, what's going to happen? Will the population, if you've got 10,000 lions and you come next month, will you find no lions, or will you find 9,000 in the next month, 8,100 or something? What would you find? What do you think? Would you expect the population to decline exponentially, or would you expect it to do something else? Let's see this, okay? No, what I'm saying is in reality, what would you expect? Is this a good model? The model says yes, but in reality, what would you expect? Yeah? Okay, so that's the key. If they eat each other, then they could decay exponentially. But if they don't eat each other, so if you had a bunch of cows and you had no grass, maybe for the next week you could count them, they just get thinner and thinner, but then they die of starvation. However, if you've got a bunch of pigs, they probably end up eating each other. So maybe for pigs, exponential decay is okay, maybe for cows it's not. But anyway, so you've got to be aware of the assumptions that go into the model. Now, you might say, okay, these are really incredibly simple models and maybe don't reflect reality very accurately. But at the time people introduced these models in the 1920s, mathematics wasn't really applied to this kind of analysis. So if you look at the history of mathematical models and when they were applied to things, basically before Newton and Leibniz, there was no calculus. And people had ideas how systems moved or changed through time, but it really took Newton, who invented the calculus when looking at the motion of objects in space, to understand how things change with time. And only after that did people start thinking, well, how can we apply this to things that change with time? And the first things they looked at was the position of stars or satellites or moons or the sun or projectiles. Projectiles were always very important because people wanted to know. They wanted to build better war machines. So lobbing huge, big objects at the opposing army was an important thing to understand. So, but then biologists started to think of, well, what happens to populations? Have you all heard of Thomas Malthus? Yeah, so he said if populations are growing exponentially and the resources are growing linearly, what is going to happen? Now, he didn't necessarily apply a differential equation to it, but later on people started doing this. And it's only going back to the 1920s that people got serious about applying these kinds of equations to understanding population processes. So this is where they began. So this is exponential decline of predator. Now, what is happening? The predator population is growing because it's taking individuals that are harvested and it's turning them into individuals of the same kind. So predators like lions will eat their prey. They will grow. Females will conceive. They'll become pregnant. They can produce new individuals, and this all takes food. And so they're extracting food at a rate that's equal to BXY. So you can say, we're going to add the biomass that's flowing out of there into here. Is that a good thing to do? Do they turn 100% of that biomass into themselves? Okay, so you have to have a conversion, which you can write as kappa B. That's a conversion parameter. So conversion rates might be If an organism is not very efficient, it may be 5 to 10%. If an organism is more efficient at converting what it extracts from its food into its own biomass, it may be 20%. And what we're going to do is we're going to just replace this with the parameter d for the time being, realizing that depending on how you choose the units of x and y, if x and y are on the same units, like kilograms per unit area, then d can't be bigger than b. D has to be smaller than b. So in this case, you have to constrain d to be less than b. Otherwise, you wouldn't have a conservation principle. You'd be making something out of nothing. The conservation principle here is that what's not extracted from here has to go somewhere else. Where does it go? So what's not extracted, where does it go? Think of it in terms of both biomass or calories. Where would some of the calories in here go in turning this into a calorific equivalent? Where would some of the calories, yeah? Well, yeah, so physiology, and that's ultimately turned into heat. So we give off a lot of heat. Now, you may not know this, but your brain is very, very expensive. It was very hard for us to evolve until we became very efficient at collecting calories. So, for example, any monkeys in the forest that eat leaves and things are not going to evolve into humans. They have to get smarter than that, and they have to seek out high-calorie food. So what's a high-calorie food in a forest? Some of these people are not answering at all. Come on, this is not a math question. Anybody can answer this. Huh? Yeah, insects are eating something that certainly, what else? Fruit, something that has a lot of sugar in it? Yeah. So we had to become omnivores, and that way we could grow a larger brain. Why do we need this larger brain? Why do you think we need it to be smart from an evolutionary point of view? Yeah, so that's a good way to put it, yeah. So we're not as strong as almost anything out there. Even if you take chimpanzees, pound for pound, the chimp is probably 3 or 4 times stronger than a human. I mean, you go and arm wrestle a 50-pound chimp, you're going to lose. And you try to outrun a leopard, you're going to lose. You try to scramble up a tree faster than any cat, you're going to lose. So we're going to lose almost everything. So we have to do something to compensate for that, and our brains help us to do that. So this is, again, mass action plus conversion. See, when you model things, you've got to think about what you're doing. You can't just write down terms. You've got to go, what are the processes? What's going on? How do we model it? So now let's go through the phase plane methodology. Okay? So if we do this, what's the first thing we have to do? We have to solve an equation, ax minus bxy equals 0. When we solve that equation, we get either x equals 0 or by equals a, which means that y equals a over b. And we can underline this in red, because we're going to plot those as red isoclines. Let's do the other one. So we're going to say cy plus dxy equals 0. So either y equals 0, or we get dy equals c. So y equals c over d. Okay? Everybody agree? So this is particularly simple, because all we're plotting here are vertical and horizontal lines. This one here. Oh, okay, yeah. So it's x equals c over d, right? Okay. So let's plot this. And this is going to be our blue isocline. So we're looking at x equals 0. This is xy plane. So x equals 0 is another one isocline. Or y equals a upon b. That's another isocline. And then the y isoclines are y equals 0 and x equals c upon d. So how many equilibria do we get? Somebody who hasn't answered yet. How many equilibria have we got? 2, okay. So one is called the trivial and the non-trivial. The trivial and the non-trivial. Okay, so now let's apply our principles to drawing arrows. So let's go over here. When y is very small, ax is going to exceed this term. So if I make y small enough, then dx dt is going to be positive. So here is, firstly we know we can draw the trajectory, how it's going to cross these lines. So because the blue line is dy dt equals 0, we have to cross here in the vertical direction. Sorry, in the horizontal direction. And because the red line is dx dt equals 0, x is not changing, and only y is changing,